Close your eyes and picture the Big Bang. You probably see an explosion, a point of brilliant light in the middle of darkness, expanding outward. A fireball rushing into the void. Matter and energy hurling themselves in all directions from a central point. This picture is in almost every science documentary, on almost every diagram, in almost every popular explanation of the origin of the universe. It is wrong in almost every important detail. The Big Bang was not an explosion. It did not happen in the middle of anything. There was no darkness around it waiting to be filled. There was no void into which the matter expanded. There was no central point. And the name itself, Big Bang, was coined by a physicist who did not believe the theory was correct, as a term of mockery. The actual story of the Big Bang, where the idea came from, who developed it, who was written out of the history of its discovery, what it actually describes, and what it does and does not tell us about the origin of the universe, is one of the most remarkable stories in the history of science. It involves a Belgian Catholic priest who was also a physicist and who understood the expanding universe before almost anyone else. It involves Einstein making what he later called the greatest mistake of his scientific career. It involves an American astronomer who got the credit for a discovery that was arguably not primarily his. And it involves a measurement so strange and so precise that it confirmed, beyond any reasonable doubt, that the universe we live in began approximately 13.8 billion years ago in a state of extraordinary density and temperature. By the end of this, you will understand what the Big Bang actually is, what the evidence for it actually says, who actually discovered it, and what the most honest thing you can say about what came before it actually is. For most of human history, the universe was assumed to be eternal and essentially unchanging. The stars were fixed in the sky. The cosmos was stable. Whatever arrangement of matter and light and darkness you could observe at any given moment, it had presumably looked much the same in the past and would look much the same in the future. This was not merely a naive popular belief, it was the considered position of the scientific community well into the 20th century. When Albert Einstein completed his general theory of relativity in 1915 and applied its equations to the universe as a whole, he encountered a problem. His equations did not produce a static universe. They produced a universe that was either expanding or contracting, a universe in dynamic motion, changing over time. Einstein did not believe this. The idea of a changing universe evolving over time seemed to him philosophically unsatisfying. He wanted his equations to describe the stable, eternal cosmos that everyone assumed existed. So, he added a term to his equations, a mathematical factor he called the cosmological constant, specifically to counteract the expansion and produce a static solution. The cosmological constant was not derived from any physical observation or measurement. It was introduced purely to make the equations give the answer Einstein wanted. He later called this the greatest blunder of his life. But in 1917, when he published his cosmological model, the cosmological constant seemed like a reasonable adjustment. There was no observational evidence that the universe was anything other than static. Within a decade, there would be. In the 1920s, astronomers were beginning to grapple with the distances of what were then called nebulae, diffuse patches of light visible in the sky, whose nature was not yet understood. Were they clouds of gas within our own galaxy? Or were they separate galaxies, vast systems of stars at distances almost beyond imagination? Edwin Hubble working at the Mount Wilson Observatory in California with the most powerful telescope in the world, established in 1924 that the Andromeda Nebula, the diffuse patch of light in the constellation Andromeda, was vastly more distant than any star in our own galaxy. It was, in fact, a separate galaxy, comparable in size to our own Milky Way, at a distance of roughly 2 million light-years. The universe was suddenly dramatically larger than it had been the day before. But Hubble was also measuring something else about these distant galaxies: their spectra. When you spread the light from a galaxy into its component wavelengths, you get a spectrum that contains specific lines, dark lines at specific wavelengths where particular elements absorb light. These lines are like a fingerprint, identifying the chemical composition of the source. And Hubble noticed that in almost all the distant galaxies he was studying, these spectral lines were shifted toward the red end of the spectrum. The red shift indicated that the galaxies were moving away from us, and the more distant the galaxy, the greater the red shift, and the faster it was receding. In 1929, Hubble published a paper establishing what is now called Hubble's law. The recession velocity of a galaxy is proportional to its distance. The further away a galaxy is, the faster it is moving away from us. The universe was not static, it was expanding, but Hubble was not the first person to understand what this meant. And the person who was first, who had worked out the mathematics of an expanding universe and drawn the correct conclusion from it before Hubble published, has spent much of the subsequent century in relative obscurity. Georges Lemaitre was born in 1894 in Charleroi, Belgium. He studied physics and mathematics, was ordained as a Catholic priest in 1923, and then studied astronomy at Cambridge and at MIT before returning to Belgium to teach at the Catholic University of Leuven. He was, in other words, both a physicist and a priest, a combination that his contemporaries often found puzzling, and which has sometimes been used to subtly undermine the scientific standing of his work. In 1927, 2 years before Hubble's famous paper, Lemaitre published a paper in a French-language Belgian journal. In it, he independently derived the equations describing an expanding universe from Einstein's general relativity, and then compared his theoretical predictions to observational data of galaxy velocities to determine the rate of expansion. He calculated what we now call the Hubble constant, the rate at which the universe is expanding, from the available data. His value was more accurate than Hubble's would be 2 years later. He sent a copy of the paper to Einstein. Einstein's response was reportedly gracious about the mathematics and dismissive about the physics. "Your calculations are correct," Einstein is said to have told him, "but your physics is abominable." Einstein still could not accept the idea of an expanding, evolving universe. Lemaitre's paper was not widely read. It was published in French in a Belgian journal by an unknown Belgian priest-physicist. The international astronomical community largely missed it. In 1931, Lemaitre's paper was translated into English and published in the monthly notices of the Royal Astronomical Society. But there was a crucial difference between the French original and the English translation. The French original contained a section in which Lemaitre calculated the Hubble constant from observational data, the priority claim that established he had derived the relationship between galaxy recession and distance before Hubble. In the English translation, this section was missing. For decades, it was assumed that Lemaitre himself had deleted the section, that he was, in the selfless spirit suggested by his religious vocation, yielding priority to Hubble. This version of the story was reassuring but incomplete. In 2011, a historian of science examined the correspondence surrounding the translation. The evidence suggested that the deletion was not made by Lemaitre himself, or at least not voluntarily. The circumstances of the omission have never been fully clarified. What is clear is that Hubble's law should, by the conventions of scientific priority, be called Lemaitre-Hubble's law. In 2018, the International Astronomical Union voted to recommend that it be called the Hubble-Lemaitre law. The vote was close. The name Hubble's law remains in common use. Lemaitre did not stop with the expanding universe. He followed the logic of expansion backward in time. If the universe is expanding, if the galaxies are moving apart from each other, then in the past, they must have been closer together, and further in the past, closer still. Follow this logic far enough back, and you arrive at a moment when all the matter and energy in the universe was compressed into an unimaginably small, unimaginably dense state. In 1931, Lemaitre published a short paper proposing what he called the hypothesis of the primeval atom. All the matter and energy of the universe, he proposed, had once been contained in a single quantum, a single point, or something close to it, which had then undergone a process of expansion and differentiation that produced the universe we observe. This was the first version of what we now call the Big Bang theory. Lemaitre was not able to work out all the details. The physics of the very early universe was far beyond what could be calculated in 1931. But the conceptual framework was there, a beginning, a moment before which the universe as we know it did not exist, an origin in an extreme state of density and temperature from which expansion produced the cosmos we observe. Einstein, by this time, had accepted the expanding universe. He had visited Hubble at Mount Wilson in 1931 and, confronted with the observational evidence, acknowledged that his cosmological constant had been a mistake. But he remained uncertain about Lemaitre's primeval atom. He found the idea of a cosmic origin philosophically troubling. The physics establishment was also uncertain. An expanding universe was one thing, observationally supported, mathematically coherent. A universe that had begun in a primeval explosion was something else. It raised the question of what had preceded it. It felt to some physicists too close to religious cosmology, a universe with a beginning, created at a specific moment. This discomfort would, in time, lead to the name. In 1949, a British astronomer named Fred Hoyle appeared on a BBC radio broadcast to discuss competing theories of the origin of the universe. Hoyle was a brilliant physicist and a committed proponent of an alternative theory, the steady-state theory, which held that the universe had no beginning, that it had always existed and always would, and that new matter was continuously created to fill the voids left by the universe's expansion. In the broadcast, Hoyle referred to the competing theory, Lemaitre's primeval atom, by then developed further by the physicist George Gamow, as the Big Bang. He intended the phrase as a dismissal, a derisive label for a theory he considered absurd. The name stuck, and it stuck in a way that has caused confusion ever since, because the Big Bang was not a bang. It was not an explosion. An explosion is matter expanding outward through space, from a central point into a pre-existing void. The Big Bang was none of these things. In the Big Bang, space itself expanded, not matter moving through space. Space expanding, with matter embedded in it. There was no central point from which the expansion occurred, because every point in space was the center. There was no pre-existing void into which the universe expanded, because space itself was what was expanding. There was no outside into which it could expand. A better analogy, imperfect like all analogies, is a balloon being inflated. Dots drawn on the surface of the balloon move apart from each other as the balloon inflates. From the perspective of any dot, all the other dots are moving away. There is no central point on the surface of the balloon from which the expansion occurs. The surface itself is what is expanding. The universe is like the surface of that balloon, except that the surface is three-dimensional rather than two-dimensional, and the universe does not exist inside a larger space the way the balloon exists inside a room. There is no outside. There is only the expanding fabric of space, and the matter and energy embedded within it. The Big Bang was not an explosion in space, it was the expansion of space itself from a state of extreme density and temperature 13.8 billion years ago. Fred Hoyle's steady-state theory was not merely an eccentric position. In the 1940s and 1950s, it had serious scientific support. The steady-state theory had certain appealing properties. It required no beginning and no end. It was consistent with the philosophical preference for an eternal, unchanging cosmos. It made specific predictions that could be tested against observation, and it had the support of several eminent physicists. George Gamow, a brilliantly imaginative Soviet-American physicist, was the principal developer of the Big Bang theory in the 1940s. Gamow worked out the physics of the early universe in much more detail than Lemaitre had, calculating the processes of nuclear fusion that had occurred in the first minutes after the Big Bang. He and his colleagues predicted that if the Big Bang theory was correct, the early universe had been hot enough for nuclear fusion to occur, and that the products of this early fusion, primarily hydrogen and helium, would be observable in the universe today. The prediction was that roughly 3/4 of the ordinary matter in the universe would be hydrogen, and roughly 1/4 would be helium, with only trace amounts of heavier elements. This is, in fact, what we observe. The abundance of hydrogen and helium in the universe is one of the key confirmations of the Big Bang theory. Gamow also predicted, in a paper published in 1948 and developed by his colleagues Ralph Alpher and Robert Herman, something else, something more remarkable. If the early universe had been hot and dense, it would have been filled with radiation, light. As the universe expanded and cooled, this radiation would have remained, cooling with the universe. Today, more than 13 billion years later, it should still be there, a faint glow of microwave radiation coming equally from all directions in the sky at a temperature of roughly 5 degrees above absolute zero. This prediction was made in 1948. It was largely ignored, and then, in 1964, it was accidentally discovered. Arno Penzias and Robert Wilson were radio astronomers working at Bell Laboratories in New Jersey. They were using a large radio antenna, originally built for satellite communications, to make precise measurements of radio signals from the Milky Way. They had a problem. No matter where they pointed the antenna, they detected a persistent hum of microwave noise, a faint, uniform signal that they could not account for and could not eliminate. They checked the antenna for equipment problems. They recalibrated. They found a pair of pigeons nesting in the antenna horn and evicted them. They cleaned out the pigeon droppings, which they described in their paper with admirable scientific restraint as white dielectric material. The noise persisted. The signal was the same in all directions. It did not vary with the time of day or the time of year. It was not coming from the Milky Way. It was not coming from any identifiable source. It was everywhere. A colleague alerted them to a preprint from a group at Princeton. Robert Dick, Jim Peebles, and others. who had independently worked out that the Big Bang theory predicted a background of microwave radiation, and who were building a detector to find it. The Princeton group had not yet found it. Penzias and Wilson already had it in their data and did not know what it was. The two groups compared notes. The hum from Penzias and Wilson's antenna matched the Princeton group's prediction precisely. The signal Penzias and Wilson had detected was the cosmic microwave background, the afterglow of the Big Bang. Light from the early universe, cooled by 13.8 billion years of cosmic expansion from a blindingly hot plasma to a faint microwave glow at 2.7 degrees above absolute zero. It was the most ancient light in the universe. It had been traveling since the universe was roughly 380,000 years old, since the moment, called recombination, when the early universe cooled enough for electrons and protons to combine into hydrogen atoms, and the universe became transparent for the first time. Penzias and Wilson received the Nobel Prize in Physics in 1978. The theorists who had predicted the cosmic microwave background, Gamow, Alpha, and Herman, did not share the prize. Ralph Alpha, who had done crucial early work on the theory while a graduate student, spent much of his career watching others receive recognition for ideas he had helped develop. He died in 2007. He was awarded the National Medal of Science in 2005, 2 years before his death, largely in belated recognition of his contributions. The pattern, again, will be familiar by now. In the decades since the discovery of the cosmic microwave background, the evidence for the Big Bang has become overwhelming, and the picture of the universe's history has become extraordinarily detailed. The cosmic microwave background is not just a uniform glow. It has tiny variations, fluctuations of roughly 1 part in 100,000 from place to place, that encode the density variations in the early universe from which all the structure we see today, galaxies, galaxy clusters, cosmic filaments, and voids, eventually grew. The pattern of these fluctuations has been mapped with extraordinary precision by satellites including COBE, WMAP, and the Planck satellite, and every measurement has confirmed the predictions of the Big Bang model. We know that the universe is approximately 13.8 billion years old, with an uncertainty of about 20 million years, which is extraordinarily precise for a number of this magnitude. We know what the universe was doing in its first seconds. In the first fractions of a second, the universe was so hot that even protons and neutrons could not hold together. The universe was a soup of quarks and gluons, the most fundamental particles. In the first 3 minutes, as it cooled, protons and neutrons combined to form the nuclei of hydrogen and helium. In the first 380,000 years, as it cooled further, electrons combined with nuclei to form neutral atoms, and the universe became transparent, releasing the light we now detect as the cosmic microwave background. Over the following hundreds of millions of years, gravity pulled together the slight density variations in the matter, forming the first stars and galaxies. Those first stars, massive and short-lived, synthesized heavier elements in their cores and scattered them through space when they exploded as supernovae. Later generations of stars formed from this enriched material. Stars like our Sun, with planetary systems including elements heavy enough for chemistry and eventually for life. The carbon in your body was forged in the core of a star that died before the Sun was born. The iron in your blood was scattered through space by a supernova explosion billions of years before the Earth existed. You are, in a precise and literal sense, made of the universe's history. The Big Bang model is extraordinarily successful. It explains the expansion of the universe, the abundance of light elements, the cosmic microwave background, and the large-scale structure of the cosmos. Every precision test has confirmed it, and yet the model as currently understood requires something deeply strange. The matter and energy that we can directly observe, the stars, the galaxies, the gas between them, everything that emits or absorbs light, accounts for roughly 5% of the total energy content of the universe. The remaining 95% is something else. Roughly 27% appears to be dark matter, matter that does not interact with light and cannot be directly observed, but whose gravitational effects are clearly present in the motions of galaxies, the bending of light around galaxy clusters, and the large-scale structure of the universe. Dark matter is not a fringe hypothesis. It is the best current explanation for a large body of well-established observations. But what it actually is, what particle or particles constitute it, is unknown. The remaining 68% is something called dark energy, a form of energy distributed uniformly through space that is driving the accelerating expansion of the universe. The universe's expansion is not slowing down, as gravity would be expected to cause. It is speeding up. Something is pushing space apart, and we do not know what it is. Dark energy was discovered in 1998 by two teams of astronomers independently, studying distant supernovae, Type 1a supernovae, which have a consistent intrinsic brightness and can therefore be used as standard candles to measure cosmic distances. Both teams found that the distant supernovae were dimmer than expected. The universe was expanding faster than it should be if gravity were the only force at work. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011 for this discovery. Dark energy is, in a sense, Einstein's cosmological constant returned, a term that describes an energy density of empty space, just as Einstein had imagined in 1917, but now supported by observation rather than introduced by fiat. Einstein's greatest blunder may have been, in some form, correct. The universe we can see and describe is 5% of what exists. 95% of the universe is, in some form, unknown. The most common question about the Big Bang is also the one that the theory, in its current form, is least equipped to answer. What happened before the Big Bang? The honest answer is, we do not know. And the reason we do not know is deeper than mere ignorance of the facts. It may be a limitation of the conceptual framework. Time, in general relativity, is part of space-time, the four-dimensional fabric whose geometry is shaped by matter and energy. At the Big Bang, space-time itself begins. Asking what happened before the Big Bang may be like asking what is north of the North Pole. The question assumes that time exists before the Big Bang, that there is a before, but this assumption may not be valid. Stephen Hawking, working with James Hartle, proposed a model called the no-boundary proposal, in which the universe began in a way that has no definite beginning, a state in which time and space smoothly merge into each other near the Big Bang, without a sharp edge or boundary at which before would be meaningful. In this model, asking what came before the Big Bang is like asking what is south of the South Pole. There is no such place. Other proposals exist. Inflationary cosmology, the theory that the very early universe underwent a brief period of extremely rapid expansion, makes certain predictions about the structure of the cosmic microwave background that have been partially confirmed. Some versions of inflationary cosmology suggest that our universe is one of an enormous or infinite number of universes, each beginning in its own Big Bang, embedded in a larger multiverse. The multiverse is a genuine theoretical possibility arising from well-established physics. It is also currently unobservable by definition and therefore untestable by current means. Roger Penrose has proposed a model called conformal cyclic cosmology, in which the Big Bang is not a beginning but a transition, one universe's end becoming the next universe's beginning in an infinite cycle. The model makes specific predictions about patterns in the cosmic microwave background. The interpretation of the evidence is contested. We do not know what, if anything, preceded the Big Bang. We do not know whether the question is answerable. We do not know whether our universe is one of many or the only one. These are among the deepest open questions in physics and philosophy. What we know with extraordinary confidence is what happened after the Big Bang. In the first seconds, the first minutes, the first hundreds of thousands of years, and the 13.8 billion years of cosmic history that followed. The universe began. We know when. We know how it evolved. We do not know why. In a radio telescope somewhere in the world, right now, the cosmic microwave background is arriving. It has been traveling for 13.8 billion years. It left its source, the glowing plasma of the early universe, when the universe was 380,000 years old and the cosmos was first becoming transparent. It has traveled in all directions ever since, through a universe that was expanding around it, cooling as it traveled, stretching from the wavelengths of visible light to the wavelengths of microwave radiation. It has traveled through regions of space that would eventually become the first stars, the first galaxies, the first clusters and filaments and voids. It has traveled through the neighborhood that would eventually become the Milky Way, the solar system, the Earth. It has been arriving on Earth for as long as the Earth has existed, for 4.5 billion years, before any eye existed to detect it, before any antenna existed to receive it. And then, in 1964, two radio astronomers in New Jersey detected it while cleaning pigeon droppings from an antenna and understood, with the help of their colleagues, that what they were hearing was the oldest light in the universe. Georges Lemaitre died in June 1966, 2 years after the discovery of the cosmic microwave background confirmed, more precisely than anything else could, that his primeval atom hypothesis had been essentially correct. He had been told about the discovery in the weeks before his death. Whether he felt vindicated or satisfied or at peace, we do not know. He did not write extensively about his feelings. He was, by the accounts of those who knew him, a quiet man who was more interested in the mathematics than in the recognition. The universe is 13.8 billion years old. It began in a state of extraordinary density and temperature. It has been expanding and cooling and differentiating ever since, forming stars, forming galaxies, forming planets, forming the chemistry that led to life, forming the life that led to minds, forming the minds that asked where it all came from. We have an answer to that question that is more precise, more detailed, and more carefully confirmed than any answer to any cosmological question in the history of human inquiry. The answer begins with a Belgian priest who understood it first and was written out of the story. And it ends with a question we cannot yet answer. What came before?